already, so that if we need to talk about them, we can. Let's just scan down, though, to number 3. We can come back to this one. This one was pretty straightforward, though, but if we need to, we can look at it. But let's take a look at 3. I have that here as well. I graphed this for you. I don't know if you did this as well. The thing that was a little confusing was this: is this a probability density function? And if it is, then determine the value of C. The only reason why it would not be a probability density function is if it was both positive and negative in the domain or in the sample space. And so if you notice this particular sample, like if this is just with C equal 1, for that sample space from 0 to 2/3, it's always negative, which means if you put a value of C that's negative, you'll flip this up, it'll become positive. So the C here is negative something or other. And then for the other one, from 1 is over here, isn't it, to 4/3, that's always positive. So you can find a value for C. So I don't know why they made a big deal or why Ross made a big deal about this being a probability density function, but especially since neither of those overlap one of the zeros. So if you had an overlap like between, say, 2/3 and 4/3, then you couldn't have a probability density function because no matter what you did, this would be negative somewhere. You can't have negative values for a probability density function. So that's with that one. I don't know if there's anything else. Let's see, number 1 was pretty straightforward. We can do that if you want to. Once you understand that, coming up with the C is pretty straightforward as well here. Nice polynomials. That's a little bit confusing there. But let's see, what about let's do 1 and 3 first. Make sure that there's no issues with those, because those are relatively straightforward. Yeah, what do you think, Alyssa? Isn't? I don't know why it wouldn't be. That's fascinating. Let me look it up. Is this global land? Okay, because I have the answer key because it's slightly different if you used the US version. It'll be a similar type of question though. But let me just see. Oh, I missed that. Oh, funny. Okay, I completely missed this positive here. Oh, I was just so focused on the function and saying, well, if you have a negative value for C, you're good. Yeah, the only way for this to be a probability density function is if C was negative. Thank you. Yeah, I guess I just need to read. Something that I'm not very good at, apparently. That's why I'm in math. Okay. So, yeah, for positive. Okay, so thank you. So that answers that puzzle as to what the big deal was. So it's a little bit bigger of a deal. I don't know. I think it would have been more interesting if they had one that spanned the 0. All right. So that takes care of that. Thank you, though, for pointing out that. Anything else from 1 and 3? Here it is. There it is. And 1 and 3 is good. Okay. So I've got the other 2. Oh, what did I write down there? Oh, I wrote down the start of the problem. Okay, so for this one, for number 4, and now these 2 are the same in both versions. I think that for Monday, they're the same in both versions as well, all of the problems. Okay, so probability x is greater than 20 is easy. That's just going to be an integral. Whoa, it's a giant blob. The integral from 20 to infinity. If you don't like infinity, you can always do 1 minus the integral from 10 to 20. Then the cumulative distribution function, that's going to equal the integral from 20 to t of, not 20, 10. From 10 to t. So just cumulative, and you can do that. But I can do it for you if you want. And then the probability, so now we have something interesting. Of 6 such type devices, at least 3 will function for at least 15 hours. So that is a binomial distribution where p is the integral from 15 to infinity of this, and n is 6, and we're looking for the probability of having at least 3, so greater than or equal to 3. Probably it would be, well, I'll just do it straightforward, because it seems like once I tell you that you should always use the 1 minus formula, everyone wants to use it. It would have been easier, I guess. There. So option 1 is to add up all those, or 1 minus the probability of 0, 1, or 2. So, but we could do any of this, any of 4 that we need to. If you're stuck on it, didn't know how to do the integral, or if you don't like infinity, we can avoid infinity. Wow. So this wasn't too bad. It's like Calc 1 stuff. It's just setting it up. It's always discouraging. Like in this class, it's always encouraging when we get to stuff. Oh, we're just doing some calculus, right? We do some Calc 1. Whereas in calculus, we get to the point where, oh, we're just doing algebra. It's so hard. Like in multivariable calculus, that's what we're doing. We're doing algebra now. In fact, Monday, it's all algebra. It's horrible. Oh, yeah, the antiderivative of that. So you just have to remember that, here, I'll just write it here. You have to remember that this is 10x to the negative 2. And then you can just add 1 to the power. So this will be negative 10x to the negative 1. I guess now that I've got that, I might as well. This will be negative 1, and this will be 10 over t. Is that right? So this is the answer to part B. Part B. But there's the antiderivative. So negative 10 over t plus 1. Oh, yeah, the double negative. I messed up. Yeah, you're right. Very nice. Part C, certainly. So once you can do that, then this isn't too bad. So let's get this probability. So this is the probability of success. Success being getting a device that lasts at least 15 hours. So either from 15 to infinity is the number of hours we're looking for. And so we'll take this and get this probability first. So I'll just skip to the negative 10 x to the negative first, evaluated from 15 to infinity. And if you don't mind, I'm going to leave off the limit as x approaches infinity, and we'll just do this in our heads and understand that that's going to be 0 minus negative 10 fifteenths. So 10 over 15 is the answer there. So that's the probability that a device will last at least 15 hours. And then, so that's the p here. So I'll put that here. P is 10 fifteenths. And then this is a binomial. So if you knew that there's a 2/3 chance that your device will last at least 15 hours, and you have 6 of these devices, and you were asked what's the probability at least 3 of them will function at least 15 hours, then you can put it all together in a binomial probability. Since you're asking me to do it, I'll do the 1 minus probability that x equals 0 plus probability that x equals 1 plus the probability that x equals 2. And so that's going to look like this. You start off with 6 choose 0 times success is 2/3. 2/3 to the 0 times failure to the 6th power. And then 6 choose 1, because one of them doesn't fail. One of them succeeds. And then 1/3 to the 5th. And then 6 choose 2. 2/3 to the 2nd. 1/3 to the 4th. There. So there it is. You know, if it's glory. You could also written it all out with the 4 its probabilities there, using binomial probabilities. All right. So it wasn't, I guess that one wasn't too bad. That makes me happy. Yeah, Stuff I gave calculus was not happy. It was sad. And it's going to get sadder on Monday, and they don't even know it. But, yeah, you can look forward to it. Anyway, well, with the algebra is what I'm saying, is there's some nasty algebra. It's not calculus, it's just algebra. Okay, so the filling station, I've got the answer, well, not the answer. I've got the method written down here. So notice what it's asking. It's asking, what is the capacity? So here's C for capacity. What capacity should you have so that the probability of exhausting your supply would be only 0.01? So we want to fill this tank up to the point where it's only going to run dry 1% of the time. So this is the probability that you will use between 0 and whatever C is, the capacity. And so if the probability of you running dry is 0.01, then the probability of you not running dry, that is having enough to cover however much you're going to use, is 0.99. So anyway, this turns into an algebra problem. As long as you can do that antiderivative, which hopefully everyone can do, is -1 minus x to the 5th power, evaluated from 0 to c, should equal 0.99. So you can solve that for c. In fact, look, I'm doing too much of it for you. 1 minus c to the 5th minus -1 should equal 0.99. So there it is, almost done. Solve that for c. Lots of negatives there. It's kind of annoying, but that's what you get. So, all right, we're happy. Maybe we're not happy, but we're content. And if you're content in French, you're happy. So let's go ahead and we'll trade here. I'll give you these. And we'll give you that. So hopefully this is a pretty easy one. It's very much like number 1. So if we can do number 1, we can do this one. There's 3. There's 3 there. Oh, you got too many. I'll come back for the homework once I get this set up. There we go. There, for the video watchers. Come get the stack. Or just sure it's not in vogue, especially if you're getting it over. So, I can get the stack later. Put this here for people who forgot. Oh, a lot of pumpkins out there. let's see how we're doing. Hopefully you're coming down the home stretch with this. Go back to the top so we can go over the answers. Are you sure? Oh, I see what you did. Something went wrong from here to here. So close. That's some arithmetic. Is there any others that I haven't got? It's always nice when you can identify your own mistake, though. It shows that you're a true mathematician. Good job. Okay, so here, let's see if I don't think I made a mistake. I got the same as most of you. So here's my thing. I know it's a little bit of a mess. So there's where I started. So I'm doing the integral of this is equal to 1. And honestly, I didn't check to see if this would work out nicely. I just figured whatever. It's just going to be a fraction of some sort. It's not a terrible fraction. So we got this. So I'm doing this integral, plugging in my limits. And then, so I plugged in my limits, and I got negative 2/27 as my value for c. And this, of course, is because if you graph this up here, you get a parabola. Looks like this. And so the negative will put it back up above the x-axis so that you end up with a nice probability density function. Okay, so there's my value for c. Once you've got your value for c, you can put it in there, and you can compute this. This is what it should look like. So if you've got that, even if you can't do your arithmetic, you're in good shape. So this is where we're starting. Now we just have to do some basic calculus, which should make everyone happy. A little bit of dealing with the fractions, but you can certainly use your calculator at any point you'd like, as long as you know how to use your calculator. Oh yeah, that's dangerous, by the way. I mean, here, let me just demonstrate really quick. Like, what is 10 plus 1 over 2? You know what 10 plus 1 over 2 is, right? It's 10.5. No, it isn't. But a lot of people on their calculators get 10.5 because they punch in 10 plus 1 over 2 instead of parentheses 10 plus 1 over 2. So yeah, it's dangerous using your calculator with all this stuff. But anyway, when we get down here, it's 31/81. By the way, one other thing I noticed on several of your papers is, at least a couple of you that had some arithmetic errors, is if you write something like this for me, 3, that's definitely wrong, because probabilities are always between 0 and 1. So if you get a number bigger than 1 or less than 0, you know something's gone wrong. You might not know what it is, but you know something's wrong. So if you get down to the end and you're like, oh, I've got 90/3 or something like that, then there's something wrong. Okay, well, anyway, let's see. Let's go to the bottom of this. I've got PowerPoint. Let me give a quick preview, though. So we've got just a couple things to do today. Number one is we want to do expected values. Expected values. That's number one. Number two is uniform distribution. So you remember with our discrete random variables, we have names for some of the distributions. We have names for distributions here because they pop up so frequently. So this one we're going to call uniform for a good reason. You'll see why. It's so expected values first, though. Let's see. Maybe I'll switch back to PowerPoint. And if I get sick of the PowerPoint, then we'll switch back to there it is. PowerPoint is here. Where is what I'm looking at? Expectation. There we go. Expectation. Yeah, that's what I want. Okay. So we have something like this, continuous distribution, similar to what we had on the quiz, except for I actually have the value of c there for you, so you didn't have to compute it with this one. And I want to know what is the expected value. The expected value of this particular distribution. So I suppose we need to know how to do the expected value. So back in the old days, when you were doing the expected value of a discrete distribution, what you did was you multiplied, so just to remind you, you take the probability times the outcome, multiply them, and then add them up. That's the way you do it. So here's the formula, by the way, is for a discrete random variable, you multiply outcome times probability, and then you add them up. This is something that hopefully doesn't, bless you, doesn't surprise you or scare you, is that when we take a discrete thing and we turn it into a continuous thing, a sum turns into an integral. So instead of adding things up, you're adding up really small intervals, if you will. And when you do a limit as the interval gets smaller and smaller, this sum will become an integral. But the structure is still the same. It's x times p of x. Here it's x times the probability density function. But the rest of it is the same. As before, we only really care about your domain, or whatever the sample space is. So getting back to this problem, this computing of e of x is really not that hard. What we'll do is we'll set up, so the expected value, so the average value, you'll set up an integral, and the integral will go from 0 to 2. Technically, it should go from negative infinity to infinity, but most of this function is 0. 0 anywhere except for between 0 and 2. So from 0 to 2, and you put an x in here, and then, whoops, 3/8 times 4x minus 2x squared. This kind of reminds me of back in the old days when you took multivariable calculus and you had to convert from xy to r and theta and do a double integral. You'd throw an extra r in there. I don't know if you remember this. Maybe, okay, maybe not. Anyway, so that was like it was called the integrating, it's this correction. The Jacobian is what it's really called, but it's like an integrating correction. So it's sort of a similar deal here. We're doing the expected value. You take the outcome, x times the probability, and the probability is this continuous density function. Now let's put it all together, make it look a little prettier, because this doesn't look good. So this is going to be 3. I'll put the 3/8 out front. There's no reason to put it inside. 4x squared minus 2x cubed. Now all of us can do this, I hope. Basic calculus thing here. Whoops, why did I put an equals there? It should be, do this. So let's see, this is going to be 4/3 x cubed minus 1/2 x to the 4th, evaluated from 0 to 2. And let's see if I can do this more carefully. So this is going to be 4 times 8 is 32. Let's see, x to the 4th, that's 16. And then the lower limit happens to be 0. So let's see, 32/3 minus 16/2, that's what, 64 minus 48, 16. So 16/6. So 3/8 times 16/6. What's that? Oh, it's just 1. Huh, very nice. Yeah, it all cancels. So that's the expected value. I suppose some of you might have expected that, knowing what the shape of this function is. Let me draw the shape of the function. This function looks like this. It's 2, here's 0, here's 1. So this particular function is symmetric, and so from 0 to 2, so you can see half of the probability is to the left of 1, half of the probability is to the right of 1. You've got nice symmetry. So you might have expected this expected value, but now we verified it. Well, now that we've got the expected value, we could also compute the variance. So to do the variance, we're going to need to go to Notability because I don't have enough room. So the variance, though, you know how to do it. You've done this in discrete random variables. So it's the same thing with continuous. You're going to do the expected value of x squared. Pull this up here. Here we go. There. Oops. Move it down there. Okay. Now I've got more room. So let's go ahead and do the variance. To do the variance, you're going to do the expected value of x squared. So here's what that looks like. The expected value of x squared is going to be the integral from 0 to 2 of x squared times the density function. It's 2x squared dx. In fact, you could put anything you want in here. You could do the expected value of x cubed if you wanted to, or x to the fourth, or x squared minus 7. Put whatever you'd like. You could do the expected value of the sine of x. Although I don't know why. I can't imagine wanting to do that for any reason. So this expected value is pretty easy. Let me go ahead and pull the 3/8 out. And then we will do 4x cubed minus 2x to the fourth. So this time we're not going to have any thirds, but we'll have some fifths. Okay, so this is going to be x to the fourth minus 2x to the fifth over 5. Okay, so this is now 16 minus 64 fifths minus 0. Let's see, 16, 64. So if we multiply, you get 80 minus 64, 16. Just a sec, 3/8 times 16 fifths. Interesting. So this cancels here and you get 6 fifths. Huh. So that's the expected value of x squared. But now to get the variance, you know the drill. The variance of x is the expected value of x squared minus the expected value of x quantity squared. So in this case, it's 6 fifths minus 1 squared, which is 1 fifth. So there is the variance in all of its glory. I don't know if we need to look at that. So I think you're going to find that the expected value, if you can do probabilities, continuous probabilities, then the expected value is easy step, not hard at all. So you're not going to have trouble with that. Ooh, I just remembered, brief interlude. I always look to the Ig Nobel Awards. I don't know if you're familiar with this, for funny statistics for my statistics class. So if you had statistics with me, most of the weird statistics that I brought up are from the Ig Nobel Awards. The funny thing, or the interesting thing about this year's Ig Nobel Award, they're awarded in September, around the time that the Nobel Awards are awarded. So this year there was a Ig Nobel Award for probability. And so I thought, oh, I got to share this with everybody in probability class. So anyway, the title, just a minute. Let me get the Ig Nobel. Here we go. Sorry, interlude. Where's my Ig Nobel Awards? Oh, here it is. Oh, there they are. So anyway, you can hardly see it. There's a chemistry prize for example, that one's boring. Where are the good ones? They're usually kind of funny, but this one at the top is the probability prize. So normally you don't get a prize for probability, but this is the probability prize for. You can go to Google Ig Nobel and you'll find this page. But it's fair coins tend to land on the same side they started. Evidence from 350,757 flips. So I looked up the paper, and this is where is it? It's references a 2023 paper. So I got the paper, and here's the paper, at least part of it. And what I found funny is, here we go, their data collection. So what they found was that if you have the coin on your thumb with heads up and you flip, it is more likely to land with heads up when it lands, interestingly. So now how much more likely? Not much more likely. I'll show you the results in a sec. But check this out, it's just funny. We collected data in 3 different settings using the same standardized protocol. First, a group of 5 bachelor students, like you guys, collected at least 15,000 coin flips each as part of their bachelor's thesis project. I don't know, that's the part that I find the most funny. It's that this, whoever it is that wrote this paper, they're like, okay, you 5, you flip your coin 15,000 times. And they videotaped it to documentary evidence. So anyway, so there's, that's a total of 75,000, and then they talk about other places they got their sample. So the final result, where is it? They have the results somewhere, or maybe it's up in the, here we can see it in the abstract maybe. So there's about, let's see, where's the confidence interval? That was kind of cool. Anyway, it's like really slight, a very slight advantage for the coin flip head. If heads is up at the beginning. Here's the right there. There's the confidence interval. Is between a 0.506 and a 0.509 probability of being the same side that it started on. So I just thought that was funny. So normally I just do this sort of jokey thing in statistics, but you guys, because of the probability prize, get a bonus. Okay, let's get back to this. So next thing we need to do is uniform distribution. So back to boring stuff. Oh no, yes, why not? We'll keep it. Let's go back to this. Okay, that's better. Okay, so uniform distributions. So expectations you're going to be fine with. We're making our way into the garden of continuous random variables. There is no such garden, although we should build a garden here, shouldn't we? It would be kind of cool to have like I don't know, these different random variables. Okay, so these are the 4 that we're going to be looking at, and really it's just these 3. Gamma is not all that important. We'll talk about it just briefly. But uniform, normal, you already are familiar with normal, you're going to get more familiar with it, and exponential are the 3 biggies. The uniform is the first one that we're going to deal with, and that one is something like this. Let me show you what uniform means. If you had to guess, if I said draw a density function that you think is uniform, oh, you should do that. Just draw a density function. So you already know what here. Let me just show you. This is normal. Oh, we go back here. Here's normal, just to remind you about your statistics. Yeah, it's reasonably visible. So you're familiar with that density function. You're going to become even more familiar with it after next week. But that is the probability density function for the normal random variable. We could put the y-axis here if you'd like, and this is the x-axis. So what I'd like you to do is just take a guess. What do you think the uniform random variable, what does that density function look like? Oh, I'm still on green. Let me change back to red. So take your guess. You've already got your guess. Good, good. So it's uniform. Like that. If you've got a straight line, that's all it is. It's just a straight line. And it's going to go along some interval of some sort. So you have something that could happen. I demonstrated this, I guess, with this cheesy example of throwing the pencil and watching the angle or whatever. You might say that if I took, let's do the pencil again. That's kind of fun. No, this doesn't really work. Let's say I had a super bouncy ball, a really bouncy ball, and I threw it as hard as I could against that wall, bounced off that wall. You know how it is with bouncy balls. When I was a kid, I remember throwing it in a room. It would bounce off one wall, then bounce off the other wall, and it would end up somewhere in between, wouldn't it? So if you did that in a room, throw it as hard as you can, bounces around, finally comes to rest, where it ends up is going to be relatively uniform in terms of the distribution from one wall to the other wall. And so in that case, we would have a uniform distribution from this wall over to that wall, 4, 5, 6, 8, 9. We're going to go with 9 meters, about 9 meters. So you have 9 meters, And so that uniform distribution would look something like this. Sorry, I shouldn't have had this. Don't put that. I'll just erase it. It would start at 0. 0 is over there. And it would end at 9. There, and here's none. And it's 0 everywhere else. So that's it. It's just a flat distribution. And in order for the area to be 1, this distribution, this density function, has to have a height of 1/9. That's pretty much all you need to know about uniform random variables. But of course, I've got an entire lesson. So I've heard that a professor is someone who can condense a 5-minute talk into a 60-minute lecture. So here's an example of a continuous random variable density function. The density function 1/10 between 0 and 10. That's a continuous density function. We'll define this a little bit better, maybe. Yeah, I guess, yeah. Well, I have a definition, but I don't know. Maybe we'll define it. So compute this probability. You can do it 2 ways. So let's do it the hard way first. The hard way is to use calculus. From 1 to 10 of 1/10 dx. You know what this is going to be. From 1 to 10, which is going to equal 10/10 minus 1/10, which is 9/10. That's the hard way. Easy way is this. So that's hard. Here's easy. I know I'm making a joke here, sort of, but the easy way is just to say, well, this is uniform. The entire range of values is 10. And I'm interested in the probability it falls within 9. From 1 to 10 is 9. So 9 out of 10. I mean, I suppose I could make it a little bit more interesting. And you could say that the easy way is to say it's going to be 10 minus 1 over 10. But once you know that this thing is uniform, it will be that simple in terms of probabilities. So of course, because it's so simple, the problems that are in the book that are uniform, they throw in like a binomial, they'll make it more difficult for you. So just be forewarned. Okay, so let's see how you do with this one. Just to contrast, I'm pretty sure you can do this. What's the probability? Let's do two different probabilities here. So see if you can compute those probabilities. First one is the probability that y is between 0 and 5 for that random variable. And you can either do it as an integral or as just the easy way. And then the same thing for the probability that you are between 9 and 15. And I will pick some randos to do this. Oh, did I do attendance? I thought I did attendance. Check. They'll get me in trouble if I don't do it. Oh, I didn't do attendance. All right. All right, good. Submit. All right, finally, let's randomize. All right, who we got? Jaren. Jaren, what do you think of this first probability? 5/12. It is 5/12. Very good. So 5/12. And this is going to be the integral, if you wanted to do it as an integral, from 0 to 5 of 1/12 dx. And I won't even bother going over that. All right, let's do the next one. We're going from 9 to 15 now. Briar, what do you think of that one? Ooh, you caught me in trying to fool you, didn't you? Very nice. Yes, it is 3/12. So if you have 6/12, then you fell for my trap. But it is 3/12 because if you do the integral from 9 to 15 of f of y dy, you actually get this. You get the integral from 9 to 12 of 1/12 plus the integral from 12 to 15 of 0. I didn't write it here. I should have done this sort of deal where it's 0 otherwise. I guess that was assumed. So very nice. Good job. Ooh, let's do this. Let's compute e of x. What's the expected value? And you can either do it the easy way or the hard way. So I bet you some of you can probably figure out what the easy way is. But if you can't figure out the easy way, the hard way is not that hard. So I'll do it the hard way though. But I'm curious to see what you guys want to do. All right, instead of just picking someone out of the blue, because I'm sure you can all do it the hard way. Um, but does anyone have a guess as to what you think it is without doing any calculus? Uniform random variable between 0 and 12. What's the average? Wow, no one wants to venture a guess? It is 6. Yeah, it's right in the middle, isn't it? I mean, it makes sense. You've got this continuous, let's see, draw this. Whoops, no, not that. Come back. Where'd it go? There it is. Yeah, draw this thing out. If you draw this, it looks like this. Here's 12. So if I draw my expected value right there, it's kind of like the normal distribution. The average, the balancing point, is right in the middle. It's right in the middle of that thing. Oh, it's kind of low, isn't it? Well, you get the picture. Well, let's do it, though, using calculus. So using calculus, you do this. You do the integral over the entire domain of x times the density function. Now we can do this one. We'll do this in steps here. Alyssa, do you know what the antiderivative of x, or 1/12 x is? Oh, nice, 20 x squared. Okay, and this goes from 0 to 12. Ooh, all right. Sarah, do you know what 12 squared is? It is 144, so that's going to equal 1/12 of 144 minus 0 squared is 0. Oh, no, where'd that 12 come from? 1/24. Sorry about that. I had 12 on my mind. Okay, so 1 out of 24 times that, which does equal 6 when you do the math. So very nice. It always, when you're dealing with a uniform random variable, you'll always end up with the endpoints, the average of the endpoints will be the expected value. Always. So there's an easy way. I'll show you the formulas in just a minute. Let me see if I have anything else before the formulas that are interesting. This one is boring. Yeah, that's boring. I don't want to do that. Okay, so here is my continuous random variable. If I don't like the way this looks, I'm going to have to go to Notability. So I typed this up years ago. So first off, this is the random variable with constant probability density functions, uniform. So this is, here, don't write all those words. Uniform. Write that if you want to write anything. Uniform. This is what the density function of a uniform random variable looks like. And this is a uniform random variable between A and B. So just to explain, back here, I'll switch back, don't worry. Back here, this was a uniform random variable between 0 and 12. The previous one was a uniform random variable between 0 and 10. The wall thing, it was 0 and 9. But here it's between A and B. So the A and the B are the endpoints. That's the most important bit, is understanding where the endpoints are of your uniform random variable. This pops up, the way it'll pop up, it seems like in your homework there are a lot of buses and trains that are arriving at a time that is uniformly distributed between like noon and 12:15 or something like that. And so you'll just have to figure out your A or your B based on that. We might have a few minutes to take a look at that stuff as it is. Will we? Depends on if we want to do these harder problems or not. Okay, so that's what uniform is. Hold on, we're not done. The expected value of a uniform random variable is, and here let me just highlight what you care about. So you care about this. You care about this, but not that. Not that either. Not that. Why is there so much? There. I guess all of that is the proof. So if you don't believe me, ooh, now it's hard to read. Let me erase that and try a different color. Maybe it's unnecessary to have a color. Yeah, we want you to be able to read it. I can read it up here. I don't know why it's so hard to read. Here, I'll just circle. That's safer. So this part is important. This, whoops, is equal to this. But everything in between, this is like, no matter what your B and your A are, this would be the correct calculation, which I've done. And if you believe that I can do algebra, cancel, you get this. So that's E of X. It turns out that the variance also has a very, specific form. It doesn't look quite as nice. You don't care about that. I won't circle it. But you do care about this, that the variance of this particular uniform random variable is that, b minus a squared over 12. As with the discrete random variables, when it comes time for a test, I will have a list similar to what I had on the last test, where I list off the density functions, expected values, variances for the random variables we go over. Although it's not going to be that helpful, to be honest. I just the way it is. It's not as helpful as with the discrete. It's really helpful. Okay, let's do one practice problem, and then we'll take a peek at the homework. I've got 3. Which one? Maybe we should just stick with the easy one. Those look fun. No, let's do the easy one. We'll do this one. Okay, so I have a uniform random variable on this interval from 0 to 250. I want to first of all find the density function, and of course by density function I'm going to focus on that part, the part that I've circled there. The other stuff, if you really want to, you can say it's 0 otherwise. Then I want you to compute a probability, come up with an expected value, come up with the variance, and if you can't remember the formula, it's okay because we can do it from scratch. It's easy. And then compute this probability. I'll explain what that actually means when we get to it. And then we'll take a peek, if we have time, at the homework. We might not. We only have 7 minutes. But the homework is, there's examples of uniform, mostly buses and trains, it seems like. Either arriving or leaving. You're all so quiet. It's so exciting, isn't it? It's such a simple thing. Zane, what do you get for f of x? What's this thing look like? It is 1 over 250. It's always going to be 1 over whatever the length of your interval. So 250 minus 0 is 250. Very nice. All right, yeah, this hopefully we could just do almost in your head. Rachel, what about the probability that x is greater than 100? Ooh, very good. So I'm going to write it out just so that everyone can see how you got that. I mean, maybe you didn't get it this way, but the length of the interval that you're interested in is 250 to 100, or 100 to 250. Anyway, that's what it means to be bigger than 100. And so that length is 150. And then on the bottom, I just have 250. That's the entire interval. So 250. You would get the same thing if you set up an integral, by the way, from 100 to 250 of 1 over 250 dx. That's going to be the same thing. All right, almost there. Expected value. Audrey, what did you get for your expected value? Wow, how'd you get that so quickly? Oh yeah, it's just the middle, right? It's the middle of the interval. So very nice. All right, next one. Evan, what about the variance? Yeah, this one's the only one that is going to require any additional calculations beyond just doing it in your head. So if you don't remember the variance formula, it's back here. There you go, down there. B minus A squared over 12 for anyone who needs it. So which, oh yeah, here we go. It's down here. There we go. B minus A squared over 12. That's the variance. All right, so what's B and A here, Evan? Okay, so it's going to be just 250 squared. Oh, over 12. Oh, I'll put a box around that. Who wants to compute that? I guess I suppose I could. 62500. Do I have enough zeros? I think I do. You could simplify that, but I don't want to. Okay, last one, and then I guess we'll just call it a day. Hope for the best. So what's this? It's a conditional probability. You have two options here, as you did before. We could do the probability that x is both greater than 50 and less than. So this is the intersection. Yeah, let me do it right. I'll do it right. You can probably figure out how to do it. There's a shortcut to this, but let's do it the right way. So this goes from 50 to 200. So remember the formula for conditional probability, you put the intersection of those two things, greater than 50, less than 200. So that's that. Divided by the probability of the bottom. X is less than 200, or the right. The right, it's always on there. Okay, so first things first, we can do the top. That one's pretty easy. We pick someone to do that. Nolan, what did you get for the probability that x is between 50 and 200? So what's the difference between 50 and 200? Yeah. It's 1/5, very good. And what's the denominator going to be? Oh, very good, 250, because that's the thing that we had up here with our thing. Good. Okay, next person. So Sarah, what about the bottom? What's the probability that x is less than 200? In other words, that's what it is, 200 over 250. And now, of course, you can cancel the 250s, and you get 150 over 250, or 3/4, or 150 over 200, which is 3/4. All right, excellent. I can't remember all the details of what I picked for your homework, but I think that there will be some word problems that refer to uniform random variables, just to warn you. And just do your best to interpret what's going on, and hopefully you'll be able to interpret and do well. All right, well, we'll see you on Monday. I hope you guys have a good, restful weekend. I'm going to turn off the recording in case you need to talk.